Welcome back, Mustangs, to another edition of No Here, No Problem. Today we're going to be working on the rules for solving exponentials and logarithmic equations, and then we're going to actually go through just a whole bunch of problems of solving them. Please have a calculator ready because that's going to help us to work through these problems here. And I want you guys to understand something. While you're doing these problems, there's really not one set of way of doing these. I'll try to show you guys both, or more than one way, I should say, of the different ways that you could possibly solve these. But you'll find that there's one way that might be easier than another way. All right, so we're going to go ahead and start working through these, and let's see what kind of happens. So there are some general rules that we use when we're solving these exponentials and logarithmic equations. The first is whenever you have multiple logs going on within the problem, try to condense them. You can't use a one-to-one property unless logs are condensed. So we'll see a couple of these where we're going to try to condense these. The second rule we're looking for is when we do have a one-to-one relationship possible, it actually makes things a lot faster in the problems. We'll go through a few problems where you can actually see the difference between a one-to-one relationship versus where you have to do some conversions. The third rule when we're doing these is if the variable is in a log, convert to exponential and vice versa. What we're saying in that instance is that when we have a like a log problem where it says log base b of x is equal to a, be ready to convert these back and forth so that it is b to the a is equal to x. The base stays the base and the a and the x just kind of swap places. The other one is like if I had b to the x is equal to a, then the conversion back to that would be log base b of a is equal to x. Again, the base stays where it is, the a and the x just swap places. And then the last one is check for any extraneous solutions if logs are involved. One of the rules that we should remember is that whenever we have a log base anything and then the of portion here, that this portion right here must be greater than or equal to, greater than 0. So what we'll see is that as we're working through this, we're going to have to go through and check for extraneous solutions. That comes from that domain restriction that we saw when we first introduced logs in this unit. So let's get started. If we look at letter A here, these are just the problems that are off to the left side here. But when we look at letter A, you'll notice I put two different columns here because there's two different ways that you could solve this. The first way is if we recognize that there's actually a one-to-one relationship that's going on here. Now, it's fine if you don't recognize it right away, but nevertheless, there is a one-to-one relationship here. If we take this 32 and we focus on it having the same base as this 2 that we have right here, I can write this as 2 to the 5th power. Once we have that the bases are the same, we can look at the powers and say, all right, well, if the bases are identical, then the powers also have to be identical. So we could just say that x has to equal 5, and we're done. That's it. One step, one-to-one relationship for the win. But what if I don't recognize that there's this one-to-one relationship? Well, the next thing that we could try is this on this right one. We could take this, as long as we have the base and this power isolated, we can do a conversion from log into exponential notation. If we do the conversion from exponent to log, the base stays the base. The of portion and what it equals are going to just swap places. So we get the 32 here, and then we're going to get x here. Throw this into your calculator, and we end up with 5 is equal to x. So tomato, tomato, it's your preference how you want to solve it. I don't care either way. Take a look at letter B. So there's two ways to solve this one. One is using the one-to-one property. One is using conversions. How do we use a one-to-one property? Well, if we take this portion that's right here and we move it over to the right side, because right now we have 2 on the left side, but nothing on the right. If I move that over, this will end up being log base 4 of x is equal to log base 4 of 8. And if we can recognize that the log base 4 and the log base 4 are the same, then what we can focus on now is just what they're equal to. The inside portion is the ofs, which says that x is just going to equal 8, and we are done. But again, let's say I don't recognize that. Let's say I'm in the mindset of, I don't know, let's go ahead and do the condensing. Well, if I condense, we should remember that subtraction will turn into division. And when that's the case, when we condense, we end up with the log base 4 of x over 8 is going to equal 0. So Again, to reiterate here, the x and the 8 here will turn into x and 8 right here, and they are a fraction because of that minus sign. So where do we go from here? Well, because the variable is tied up inside of log, this is where we switch it over to the exponent notation. So if we do that, we get 4 to the 0 power is going to equal x over 8. Remember, the base stays the base, and the other two just swap places. Anything to the 0 power is just going to equal 1. So we have x over 8 is equal to 1, which means that x equals 8. So there's no right or wrong way in this one. You can see that one way definitely gets through there a lot faster. Doesn't matter, though, up to you which way you want to do it. All right, let's take a look at letter C. Hopefully you notice here that this is a lot like the last one where we have a one-to-one relationship possible here. If I take this and move it over, we end up with natural log of x is equal to the natural log of 3. And then we could say, well, my bases are the same, my natural logs are the same, and so I could just say that x is equal to 3. And if we go ahead and try to do the other route where we don't recognize it's a one-to-one, we're going to go ahead and put these together. That minus will go ahead and turn into a division with the x and the 3. So we're going to have natural log of x over 3. X over 3 is going to equal 0. And again, that x over 3 comes from the x and the 3 on the top there. And then what we're going to do is we're going to do the conversion. Now, if you remember, the base of natural log is always e. That means that when we do the conversion from natural log, where you're going to use a base e, so base will be e, to the 0 power is equal to x over 3. Just remember that these two will always just swap places, and that's how we end up with the switched positions. And then we say e to the 0 power. Anything to the 0 power is just 1. X over 3 is equal to 1, so x is going to equal 3. And for letter D, same thing. We could technically use a one-to-one property here. Now, this one's a little trickier. This one is a little trickier, but it is possible to use a one-to-one. If we look at this right here, 1 over 3, well, that is actually the same as 3 to the negative 1 power raised to the x. And the 9 can be written as 3 to the 2nd power. That means that once my bases are the same, I could focus on the powers. We have negative x is equal to 2, which means that x equals negative 2. Now, this is our first one where we get an x that's equal to negative. And if you recall, back in the rules at the top here, I said that we cannot have negatives. Well, I didn't really say that. I said we have to check for extraneous solutions if logs are involved. When we look at this one, there were no logs involved. So there was nothing that I have to actually deal with. X is just going to equal a negative 2. Let's check this way, though, if I do it differently. Let's say I didn't recognize that one-to-one, because this is a little tougher to see that one-to-one. We can go ahead and still do the conversion from exponent into log. And so if we recall, when we're doing this conversion, we have the log base of equals. And the conversion here is the base stays the base. So base stays base. And then the x and this spot are going to switch, and the 9 and here are going to switch. So you're just filling in those spaces there, okay? So we're going to have log base 1/3 of 9 is equal to x. And so all we have to do is throw this in the calculator. We can get that x is equal to a negative 2. Now, there's no domain restrictions here, because when I put in a negative 2, I'm not going to be putting it inside of the log. I don't have a variable inside of the log. And so it's okay. We don't have to check for anything extraneous. We're good here. Take a look at letter E. This is one, I split it up, but I wanted you guys to think about it. Is there possibly a second way you can do this? Yes, but I'll show you both ways just for the heck of it. So the variables in the exponent, let's convert it to log. So we're going to have natural log, base of E, 7 is equal to x. We don't normally write this e that's in here because it's actually redundant since natural log's base is always e. That means natural log of 7 is going to go ahead and be our value here. So let's go ahead and at natural log 7, we get that x is equal to 1.95. I'm just going to go to 2 decimal places. How do we go about using other methods and properties? I can't use one-to-one, but here's what we can do. We can use a rule that says I can take the natural log of both sides of this function. And if I do that, what we're going to end up with is natural log of e to the x equals natural log of 7. We could take the x and move it up front, and this makes it x natural log e is equal to natural log 7. And if you recall, one of our properties that we discussed before is that the natural log of e is just equal to 1. And that's really because of change of base here, because what's going to happen is the natural log of base is e, and we're taking of e. And if I did the change of base, we'd have natural log e divided by natural log e. That's just 1. So we end up with x is equal to natural log of 7. And again, that still is going to be 1.95. All right, letter F. We're going to have the conversion. We're going to go e to the negative 3 is equal to x. So we put that in e to the negative 3. We're going to get that x is equal to 0.05. Normally, I would go probably a few more decimal places with these. I would normally go about 4 decimal places. But for the sake of the problem, I'm just putting it to 2 for right now. All right, let's take a look at letter G. Doing the conversion here, we're going to go ahead and do 10 raised to the negative 1 is equal to x. So we're going to get 1 over 10 is equal to x. Honestly, I can't really think of another way that we could do letter G that is really worth even going through. So let's just go ahead and leave that as it is. Letter H, we're going to do our conversion here. 3 raised to the 4th is going to equal x. So that means that 81 is going to equal x. Base stays the base. The other two parts switch places. All right, so let's look at more examples here. We have, let's see, down in this one, e to the x is equal to 72. We're going to have natural log of base e, 72 is equal to x. I don't have to write that e. Again, it's redundant too because of the fact that we do have natural log, so the base is going to be e. Natural log of 72 is going to equal x equals 4.28. Take a look at letter B. Now, this is the first one where we actually have a little bit of work to do. It's not too much, but it's just a smidge. Whenever we're trying to do the conversion, remember what I said that we always have to have this portion isolated. We have to get the power and the base isolated before we can actually do any sort of conversions. So this means that we have to take this 3 and get rid of it. Since we have 3 times, that's not the right button I wanted to push. Since we have 3 times the quantity 2 to the x power, instead of multiplying by 3, let's divide both sides by 3. When we divide both sides by 3, we have 2 to the x is going to equal 14. We can't use the one-to-one property here, so we'll go ahead and do our conversion over to log, which means we'll have log, the base stays the base, the 14 and x swap places. So 14 and that equals x. And I'm going to throw this into my calculator here. We get 2, 14. So we end up with x is going to equal 3.81. All right, let's move on. So this one says solve each logarithmic equation. I'm going to do this one first over here. Natural log of 3x is equal to 2. This really should probably have a parentheses around it just so we understand that this is grouped together. So the base of natural log is e. Converting it to get that x out of it will be e to the second power is going to equal 3 times x. And then to get x by itself, we're going to divide it by 3. And so the answer for this is e to the second divided by 3, which you could just throw into your calculator, and we're going to get that x is equal to 2.46. Going over here, hopefully clear as day, we can see that there's a one-to-one property here. Now, there's some disclaimers here since we're solving, and we have variables inside this red portion here. One of the rules is that when we have that red portion there and the variables inside of that, we cannot have a negative. 5x minus 1 has to be greater than 0, can't even equal 0. And so just remember that this can't be negative, it cannot equal 0 either. Same thing with this portion over here. It cannot be negative and it cannot equal 0. So these are domain restrictions we're going to have to check for in a minute. Now when we look at this, log base 3 is on both of them. That means we have the one-to-one property, so I could just say that 5x minus 1 is equal to x plus 7. Go ahead and do your normal steps for solving. We get that x is going to equal 2. When I check that 2 works, we can do 5 times 2 minus 1, which means that we have 10 minus 1, which is just 9. That side is good. And when I put in a 2 here, 2 plus 7 equals 9. That also is good. So we are okay. We didn't violate any extraneous solutions here. Let's take a look at a problem where there might be one. All right. So when we look at this, obviously you want to try to use one-to-one property, obviously. Well, right now when we look at this, there's two terms here and there's only one here, which means we don't have a 2-to-1 ratio going on here. I'm sorry, 1-to-1 ratio. We have a 2-to-1 ratio. So to take those two that are on the left side, this is where we're going to use our rules of condensing. That plus that's right there is going to turn into a multiplication instead. So we're going to have log base 2 of x times x plus 2. So we're going to take those two parts, we're going to multiply them together. And it's going to equal log base 2 of x plus 6. Okay. Now before we move on with this, I forgot to actually mention right away in the beginning there that we should check for domain restrictions. X has to be greater than 0 here. X has to be greater than -2. And x has to be greater than -6. All right. Anything that is going to violate this means that we have an extraneous solution within the problem. We will go back and check in a moment here. So we should see a one-to-one relationship, which means now I can just focus on the insides. So we have x times x plus 2 equals x plus 6. We have x squared plus 2x equals x plus 6. If we continue solving, we have x squared plus x minus 6 is equal to 0. Factor this, we have x plus 3 and x minus 2 is equal to 0. And then we're going to solve, we have x equals -3 and x equals +2. Let's check it. Let's see if we violated our domain restrictions anywhere with any of these parts here. Okay. If I was to take a 2 and plug it in right here, we're good. It's a number that's bigger than 0. If I take the 2 and plug it in right here, we're going to have 2 plus 2, which is 4. We're good. If I take the 2 and plug it in here, we're going to have 2 plus 6, which is 8. We're good. So that 2 is definitely one of our answers for this problem. We're good with that 2. But let's check what happens when we use our -6. That -6 goes in right here. We have a negative. We just violated our domain restriction. Now, I don't even have to check the other answers. We know right away that that's not going to work. So we can go ahead and omit that. And -6, is a extraneous solution. All right. All right, investment time. So I went through and started this early and highlighted the key parts. I would recommend you guys do the same thing so that you kind of know what's the information we're looking for. In this case, they're telling us to go ahead and compound it continuously. That means that right away we should be using the formula A is equal to PERT. That means compounded continuously. When we start this problem, we are saying that we're going to take and deposit $500. So the modification to this formula now is that in place of our P, we're going to go ahead and put $500. It says it's going to go ahead and double, which means that's our end amount. And then we're given our rate here, which is 6.75%. So the T is what we're going to end up solving for here. So let's plug in the parts that we know. The 500 is going to go in for, what we started with. The A is what we're going to get when we double it. Well, think about if you double it. I put in 500 and I double it, I'm going to have 1,000. If I put in 2,000, I'm going to have 4,000. So you're doubling it. Let's go ahead and throw in the doubled amount, which is 1,000. Then we have E. Let's look at the rate here. The rate is going to be 6.75. Now, the common mistake that people make is that they use 6.75 as the value. Okay. What that really is that means you're using 675% for the interest rate. If you can get 675% for the interest rate, you should retire early because you're really good with money. So that's the mistake. But what we should use is 6.75% as a decimal is actually 0.0675. That's the correct decimal value to actually use for the rate. So we're going to use 0.0675, and we are going to go ahead and solve for T, because it asks you how long. So standard protocol for all these problems is that we're going to take and isolate this portion first so that we can go ahead and solve for T. If I divide both sides by 500 to get rid of that quantity that's right there, that's going to leave me with a 2. That should make sense since we said we doubled. And we're going to have e to the 0.0675t. To get the variable out of the exponent, we do the conversion, log into log. And we're going to actually use natural log here. The base stays the base. The other two parts swap places. So we're going to have a 2 and then 0.0675t. I don't need that e there. It's redundant to do that, excuse me. So we'll do natural log of 2, and whatever we get there, we'll divide it by 0.0675, and we end up with the t is going to equal 10.27 years. That is it. I know I went kind of quickly through some of these problems, but they are supposed to be really quick problems. If in the event there was one that you missed, I encourage you to please go back, watch anything that I went through too quickly by. Try every problem the best you can. Let me know if you have any questions, but I know you guys are going to rock it. So anyways, you guys take care and have a good one.